So we've got another proof question here. So we have our assumption. Suppose A and B are n by n matrices with AB equal to negative BA. So not quite commutative, but something close to it. And what we're trying to show is that if n is odd, show that either A or B has no inverse. So we've got this assumption. A and B are these n by n matrices with this property. There's actually technically another assumption to this if we're going to make this conclusion. So if n is odd, this is a second assumption. We want to establish this conclusion, show that either A or B has no inverse. So this is what we need to figure out. This is actually, it's quite a tricky one. It's kind of an interesting one, but also a fun one at the same time. There's obviously a pretty big giveaway as far as what approach you might take just by virtue of what chapter this question falls in. But there might be some other ways we could get to the same conclusion. We're trying to make this conclusion that A or B has no inverse. We certainly know that if A or B, if we're trying to establish that something has an inverse, or if we're given this property that it has an inverse, that's often something that we can work with nicely by just saying, here's the inverse, let's play with it. In this case, the property of no inverse is a little bit dicier because we don't have as nice a conclusion from it. But having no inverse, and again, this chapter is a big clue for this. There's something that can very, very nicely mathematically be tied to this. It does mean that the determinant of A is 0 or the determinant of B is 0. So one of those, if one of those doesn't have an inverse, then that means they're not invertible. It means that one of them does have a determinant of 0. And so this is probably how we want to play around with the information that's given to us, or these assumptions that are made. So we're told that AB equals negative BA. We're going to actually just kind of lose a whole bunch of information and look at the determinants of these. If these are the same matrix, AB is negative BA, then we have that their determinants are the same. So the determinant of AB equals the determinant of negative BA. And as we know, it's not just as simple as saying negative the determinant of BA. We don't just get to pull scalars out like that. So that does not work. I'm going to just scribble it out in red. That's not the case. If we are multiplying this whole BA matrix, remember what that means is that every row gets multiplied by -1. And if every row is being multiplied by -1, remember that's a row operation whose effect is actually multiplying the determinant by -1. There's 3 rows because B and A are both 3 by 3 matrices. So effectively what this is going to do is multiply by -1 3 times. So what it actually is, oh, sorry, it's not 3, it's n rows. I should be careful with that. There's n rows in this matrix BA because they're both n by n. So just to highlight that there. So we actually have to multiply the -1 by n, not 3, which is fixed. So what we'll get is -1 to the n of the determinant of BA. And we have some other properties that we do get to use here. The multiplicative property of determinants. So what I can actually do is apply that to say then that the determinant of A times the determinant of B is equal to -1 to the n times the determinant of B and the determinant of A. And here, if n is odd, so we do get to make that assumption now, and that's, I think, kind of why in my mind I went with the number 3. But if n is odd, then -1 to the n is -1. So we do get to use that. So the determinant of A times the determinant of B is equal to negative of the determinant of B times the determinant of A. And the only way that, again, the thing on the left and the right are the exact same except the negatives. So the only way that a number is equal to its negative is if that number is, well, 0. So a nice conclusion that we can actually make from this. Well, I'm trying to move some stuff around here. So just squeeze things a little so that I have a little bit more room. But yeah, so the only way that these two sides are equal to each other, making note of the fact that this and this are the same thing, is that we must actually have that those green chunks are actually equal to 0. So therefore, the determinant of A times the determinant of B is equal to 0. If you want to see it algebraically, I mean, just move one to the other side, and you've got 2 times the determinant of A times the determinant of B is equal to 0. It's the same conclusion. This implies that one of the determinant of A or the determinant of B is 0. And that means that one of, I should say at least one of, A or B is not invertible. And that concludes the statement that we're trying to establish here.